Let's talk about the first problem. So you're gonna solve two different problems. So in this video, I'm solving a problem related to the force, and in this problem, you will see that actually the scale, the bathroom scale, whatever you are taking the weight, taking your weight, actually measures the normal force. Okay, so here is a problem. So tourist in the Hoover Dam elevator. If you visit the Hoover Dam, it's fantastic. And the tourist is taking his weight when going through the elevator in that observation tower. A tourist with a mass of 70 kilogram is standing on a digital scale inside the Hoover Dam observation elevator. Number A, yeah, the elevator descends at a constant speed of 2 meter per second. What does the scale read? Number B, yes, the elevator accelerates downward at 1.2 meter per second square acceleration. What does the scale read? Number C, yes, the elevator slows to a stop while moving downward at 1.5 meter per second square. What does the scale read? So what do you think? All the time the scale has the same value, or the scale's reading changes when accelerating, when speeding up, when slowing down, when going up, going down? What's going to happen? Okay, let's do this problem, then you will realize. Okay, let's solve this problem here. The mass of the tourist here is 70 kilogram, and you know the acceleration due to gravity is 9.8 meter per second square. And now we have to first of all find out the digital scale that shows the weight of that person which is in the Hoover Dam observation elevator. In number A, the elevator is descending with a constant speed of 2 meter per second. Then we need to find what does the scale read. So the object of interest in this case is the tourist, right? The tourist weight when in the elevator is pointing downward toward the center of earth. So weight force exerted by earth acts on the tourist is WET. And this elevator is not accelerating, it has a constant speed. That means the velocity is in downward direction, which is 2 meter per second, but the acceleration is zero. If acceleration is zero, right, net force must be equal to zero because of the second law. Now if net force is zero, then the normal force from the scale to the the scale to the tourist, or you can say the normal force from the floor to the you know to the screen is now you can see here the normal force exerted by the spring on the scale is upward, that is NST. So now weight on the the tourist, weight of that tourist, now weight of that tourist must be equal to the normal force acting here. Okay, so the net force is zero in this case, isn't it? That means the normal force plus weight force, that makes the net force. But look at the sign, here. So in our sign convention, anything going right, anything going up is positive, anything going left and anything going down is negative. So the normal force is going up, it's positive, weight force is going up, that is negative. So we can write down the normal force minus weight force is equal to 0. This can be written as normal force is equal to the weight force, then weight force is equal to the mass times gravity, acceleration due to gravity. So in this case, mass is 70 kilogram, g is 9.8 meter per second square. If we calculate this, we will get 686 Newton. So when the elevator is not accelerating, only going with the constant speed, constant velocity, then the normal force that the scale reading shows, right, is equal to the real weight of that person. That is the real weight of that person, okay? The real weight of that person, of that tourist. But now, part B, you have the situation changes. The situation asks that yes, the elevator accelerates downward at 1.2 meter per second square acceleration. What does the scale read now? Now you have the acceleration. So again, you have the weight of that tourist. Now you have the acceleration is downward. Then the net force must be downward because the direction of the acceleration is the direction of the net force. So to have the net force downward, then the normal force must be shorter than the weight force. Okay, normal force we use st, so nst. So use the second law of motion, F is equal to mass times acceleration. Again use the coordinate system, right? Anything going right and up positive, anything going left and downward negative. So what makes the net force here? Again the weight force plus the normal force, which is equal to mass times acceleration. Now we need to take care about their direction because we are dealing with the vector quantity. So weight is vector, so this is negatives, that's going downward. Normal force is positive direction, you see here, but the acceleration is negative because it is going downward. So these equations looks like this. So weight minus weight plus normal force is equal to the mass minus mass times the acceleration. So the scale rate the normal force, which is equal to mass times acceleration plus weight force. Now you can see here, which is equal to the mass times acceleration plus mass times acceleration due to gravity. Weight is this mass. So plug everything here. What you will get is, we can take the mass common, that is the g minus a, right? So mass is 70 kilogram, g is 9.8 meter per second square, acceleration is 1.2 meter per second square. If we do that, we will get, so this is 70 kilogram multiply by 9.8 minus 1.2, that gives 8.6 meter per second square. So kilogram meter per second square Newton, so you will get 602 Newton. You see here, the real weight of that person is 686 Newton. But when that person inside the elevator, then if he try to take his weight using the scale only shows 602 Newton. Okay, 602 Newton. When things are not accelerating, the scale gives the correct real reading. If it is accelerating, you see here, it now decrease the reading. But here is the situation 3 that we call number C. What it says is, yeah, the elevator slows to a stop while moving downward at 1.5 meter per second square. So how do you deal this problem? Let me write down here. Now again the weight of that tourist is downward. Now here the acceleration is must be upward because this is slowing down. The velocity of that elevator is downward because it is descending. in the Hoover Dam observation tower, if velocity is downward, if it is slowing down, then acceleration must be upward. We discussed that thing in our kinematic problem, right? So to have the acceleration upward, then the net force must be upward. To have the net force upward, then the normal force must be greater than the weight force, isn't it? That's how you have the acceleration upward. So again, the net force is equal to mass times acceleration. Net force is again the normal force times weight, sorry, addition with the weight force, which is equal to mass times acceleration. So again, we have to take care about the sign. So all the plus sign here, because the acceleration is upward positive, weight is negative, this is positive. So that means the normal force minus weight force is equal to mass times acceleration. Again, the scale read the normal force, which is equal to mass times acceleration plus weight. So nst is equal to mass times acceleration plus weight is mass times gravity. So that is equal to mass is equal to acceleration plus gravity. So it slows down, then your scale shows the higher value. Let me plug everything here. That is 70 kilogram. Let me use my calculator here. This is 70 kilogram. Acceleration is now 1.5 meter per second square. Acceleration due to gravity is 9.8 meter per second square. So that is 70 kilogram multiplied by 11.3 meter per second square. If we calculate that, I will get 791 Newton. Now it seems that your weight increased, right? 791. So that's why these two weights, 602 Newton and 791 Newtons, are apparent weight. Apparent weight, okay? Not a real weight. So you now know that the scale from which you are taking your weight is measuring the normal force. If it is not accelerating, that normal force can be translated into your real weight. That's the physics here. Okay.